beneath your feet right now, somewhere on this planet, a vast and silent world is slowly breathing. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That world is made of water and ancient plants and time. More time than you can easily hold in your mind. It stretches across roughly 3% of all the land on Earth. That may sound small, but 3% of all land on Earth is an area larger than India. These are the peat bogs, and most people walk past them, or over them, or fly above them without ever knowing what lies just below the surface. Picture the northern parts of the world: Canada, Russia, Ireland, Scotland, Finland. Imagine flying low over those places on a gray morning, the lights soft, and even the ground below you a deep, dark green. Not the bright green of a forest. Something older, something quieter. The ground looks spongy from above, almost like a living skin stretched across the earth. In places, it shimmers where shallow water pools between cushions of moss. In other places, it is flat and open and still, stretching to the horizon without a single tree. That is a bog, and it is one of the oldest living systems on our planet. Peat bogs have been forming for around 12,000 years. That takes us back to the end of the last ice age, when glaciers pulled back from the land and left behind cold, wet hollows filled with meltwater. Life moved in slowly. Mosses came first, then more mosses, and those mosses never fully died. They piled up layer on layer, century on century, in water so still and cold, and starved of oxygen that the normal process of decay almost stopped entirely. What you get after thousands of years of this is peat. Peat is a soft, dark, spongy material made of partly broken down plant matter. It feels dense in your hand, almost like wet earth. It is not soil. It is something closer to the very first stage of coal. It holds water the way a sponge does. In some bogs, the peat layer is more than 10 meters deep. That is deeper than a 3-story building is tall. And it holds something extraordinary inside it. Time. Every layer of peat is a record. A page in a book that no one wrote on purpose. Pollen from ancient ancient flowers drifts down into the still water and gets locked in place. Seeds fall in and stay. Insects land on the surface and sink. Even the air itself, trapped in tiny bubbles, gets preserved. Scientists can drill down into a peat bog and pull up a core of material that reads like a diary of the last 10,000 years. They can see which plants grew in which century. They can see when the climate shifted. They can see the ash from volcanic eruptions that happened before any human wrote a single word. The bog does not forget. What makes this possible is the extraordinary stillness of bog water. It is cold. It is deeply acidic, meaning it has a sharp, low pH like vinegar, which slows the growth of the bacteria that would normally break things down. And it carries almost no nutrients. Most living things struggle in those conditions. But the bog has built its whole world around them. The plants that thrive here are specialists. They have learned over millions of years of evolution to live on almost nothing. The result is a place that feels unlike anywhere else on Earth. Stand at the edge of a large bog on a still morning, and the silence is thick. The ground gives slightly under your feet, like walking on a mattress. The air smells faintly of earth and water and something older, something you cannot quite name. The colors are deep and muted: dark amber water, rust-red moss, pale green cushions of sphagnum spreading in every direction. It is not dramatic in the way a volcano is dramatic, or a waterfall, or a thunderstorm. Its power is quieter than that. The bog works slowly. It builds itself one thin layer at a time. It stores carbon that has been pulled from the air over thousands of years. It holds water that would otherwise flood the land downstream. It keeps the past perfectly preserved in its cold, dark depths. Everything here is connected to everything else. The rain that falls, the moss that grows, the water that never drains away, the ancient air locked in the deep layers below. It all fits together with a kind of slow, patient logic that took the earth thousands of years to build. And it is still building now, tonight, while you sleep. A bog begins with water that has nowhere to go. Picture a low, flat place in the land. Rain falls. places, the soil beneath is made of dense clay or solid rock. The water can't drain down. It can't drain sideways either. So it just sits there, pooling in the hollow, year after year. That still, standing water is where a bog's long life begins. Not every wetland is a bog, though. Swamps have trees. Marshes have reeds and grasses that sway in the wind. A bog is different. A bog gets almost all of its water from rain and snow alone. No rivers feed it. No underground springs push water up from below. Scientists call this kind of wetland ambrotrophic, which means fed by rain. The bog is entirely at the mercy of the sky. Whatever the clouds bring, that is all it gets. Because of this, bogs are found in places where rain falls often and steadily. The cool, wet climates of northern Europe, Canada, and Siberia are perfect for them. Ireland is covered in bog. So is Scotland. So are vast stretches of Finland, where bogs cover nearly a third of the entire country. In Canada, boggy wetlands called muskeg stretch across millions of square kilometers of the north. If you could walk from one end of Canada's muskeg to the other, you'd walk farther than the distance from New York to Lowe's Angels and back again. Bogs grow slowly, very slowly. A single meter of peat, the dark spongy material that builds up at the bottom of a bog, can take 1,000 years to form. Think about that for a moment. 1 meter, 3 feet, the height of a kitchen counter. 1,000 years of slow, quiet accumulation. Some bogs in Ireland and Scotland are 8 or 9 meters deep. That means the peat at the very bottom started forming before the ancient Romans built their roads. The material that makes up peat is mostly dead plant matter that never fully broke down. In most places on Earth, when a plant dies, it rots. Bacteria and fungi get to work. Within a few years, the plant is gone, returned to the soil. But in a bog, the water is cold, low in oxygen, and highly acidic. Those conditions slow decomposition almost to a stop. Dead plants pile up, layer upon layer, century upon century, like pages in a very old book that no one has ever opened. That acidity is one of the most important things about a bog. The water in a typical bog has a pH of around 4. For comparison, pure water has a pH of 7, which is neutral. A bog's water is close to the acidity of tomato juice. Most bacteria can't survive in conditions that acidic. That's why things don't rot. That's why the bog preserves everything it catches. The surface of a bog looks soft and gentle. It's often covered in a thick mat of moss, pale green and golden, with small pools of dark water scattered across it like mirrors. In the right light, those pools reflect the sky perfectly. The whole surface can feel springy underfoot, almost like walking on a very thick mattress. But beneath that soft surface, the peat goes down and down, dark and dense and cold, holding thousands of years of the world's quiet history. Bogs cover about 3% of Earth's total land surface. That might sound small, but 3% of all the land on Earth is an enormous amount of ground. All the world's bogs together cover an area roughly the size of India. And within that vast, dark, waterlogged ground, bogs hold an astonishing amount of carbon, the chemical element that plants pull from the air as they grow. Scientists estimate that peat bogs store twice as much carbon as all the world's forests combined. Even though forests cover far more land, that fact alone tells you something important about what a bog really is. It's not just a wet, muddy place. It's a slow machine, a patient, ancient system that has been quietly doing its work for thousands of years, pulling carbon out of the air, locking it away in the cold dark, keeping the world in balance. Every layer of peat is a record. Every centimeter is a century, and the bog just keeps building, one quiet year at a time, in no hurry at all. The world moves fast. The bog does not. And in that slowness, there is something worth paying attention to. At the heart of every peat bog, there is a single plant doing almost all the work. It doesn't have flowers. It doesn't have roots in the way most plants do. It's small, soft, and pale green, and it has been reshaping the surface of the earth for hundreds of millions of years. Its name is sphagnum moss, and without it, peat bogs simply would not exist. Sphagnum looks delicate. Up close, it forms dense, spongy cushions that feel almost like wet velvet beneath your hand. shifts depending on the species. Some are bright lime green, others are deep rust red, and some glow a soft golden yellow in the afternoon light. There are around 380 known species of sphagnum across the world. Each one is slightly different, but they all share the same quiet, extraordinary power. What makes sphagnum so remarkable is its structure. Each tiny leaf is made up of two kinds of cells packed tightly together. The first kind are living cells that carry out photosynthesis, the process by which plants turn sunlight into food. The second kind are dead cells, large, hollow, and empty. These dead cells act like tiny water tanks. They can hold up to 20 times the plant's own weight in water. Think about that for a moment. A single handful of sphagnum moss can hold as much water as a soaking wet sponge many times its size. This ability to hold water is the first key to how a bog is born. When sphagnum grows in a wet place, it drinks in water and holds it close. The ground around it stays saturated, completely soaked through. Other plants struggle in these waterlogged conditions, but sphagnum thrives. It grows upward, layer by layer, slowly lifting itself above the standing water below. As it grows, sphagnum does something else that changes everything around it. It releases hydrogen ions into the water, tiny charged particles that make the surrounding water more acidic. This is not a small effect. Sphagnum can lower the pH of its environment dramatically, turning a relatively neutral pool of water into something as acidic as vinegar. The bog becomes a place where most bacteria cannot survive, and without bacteria, dead plant material cannot break down. It simply accumulates. It piles up. It becomes peat. This is the origin story of every peat bog on Earth. It begins with sphagnum, and sphagnum's two quiet gifts, the ability to hold water and the ability to acidify everything around it. These two forces, working together over centuries, create the conditions that make a bog possible. Sphagnum grows slowly. Most species add only a few millimeters of height each year, but it never really stops. The living moss grows upward at the top, while the dead material below it compresses and darkens into peat. Scientists estimate that it takes around 1,000 1,000 years for a bog to accumulate just 1 meter of peat. The bogs we see today, some of them 10 meters deep or more, represent tens of thousands of years of sphagnum doing its quiet, patient work. What's extraordinary is that sphagnum doesn't need rich soil to do this. In fact, it prefers poor conditions. It thrives in places where nutrients are scarce, where the water is cold and still, where other plants give up. Sphagnum gets most of what it needs directly from rainfall. It is what scientists call ambrotrophic, a word that means fed by rain. The bog it creates becomes an island of water in the landscape, raised above the surrounding ground, sustained entirely by what falls from the sky. This is why bogs form in cool, wet climates. The west coast of Ireland, the highlands of Scotland, the vast boreal forests of Canada and Russia, the cold plains of Scandinavia. These are the places where rain falls often enough and temperatures stay cool enough for sphagnum to outpace decay. The moss grows faster than the dead material beneath it can rot away. And so the bog rises. There's something almost impossible to believe about this. A plant no taller than your finger, with no roots anchoring it to the ground, has built some of the largest ecosystems on Earth. The great peat bogs of Siberia stretch across millions of square kilometers. The raised bogs of Ireland hold carbon that has been locked away since before recorded history. All of it traces back to sphagnum. All of it began with that soft, pale cushion of moss, drinking in the rain, acidifying the water, and slowly, patiently, building something that would last for ages. The moss doesn't hurry. It never has. It simply grows, and in growing, it changes the world. Water is the heart of the bog. Everything that makes a bog strange and wonderful begins with water that has nowhere to go. Most wetlands sit in low places where rivers and streams flow in. The water moves. It carries minerals from the surrounding land. It brings nutrients. It connects to the wider world. A bog is different. A bog is fed almost entirely by rain and snow falling directly from the sky. No rivers feed it. No streams trickle in from the hills. The water that fills a bog arrives from above, and then it stays. Scientists call this kind of wetland ambrotrophic, which means Because of this, the water inside a bog is remarkably pure in one sense. It carries almost no dissolved minerals. Rainwater is naturally soft. It lacks the calcium, magnesium, and other minerals that most living things need to grow. When that rainwater pools in a bog and has nowhere to drain, it creates a world that is mineral poor in a way that almost nothing else on earth can match. That mineral poor water is cold and still. In the deep layers of a bog, the water barely moves at all. There are no currents, no circulation. Oxygen, which normally enters water through movement and mixing, cannot get in. The deeper you go, the less oxygen there is, until the water at the bottom of the peat is almost completely without it. Scientists call this condition anoxic, meaning without oxygen. It is this stillness, this quiet absence of oxygen, that gives the bog its most remarkable power. Without oxygen, the tiny organisms that would normally break down dead plant material cannot survive. On a forest floor, a fallen leaf disappears within a year or two. Bacteria and fungi consume it. Insects shred it. Rain washes the last pieces away. In a bog, a fallen leaf may still be recognizable decades later. The chemistry of the water slows decay almost to a stop. The bog does not consume what falls into it. It holds it. The water itself takes on color over time. As sphagnum moss and other plants slowly release compounds called tannins and humic acids into the water, the bog water turns a deep, rich brown. It looks like strong tea. In some bogs, the water is so dark you cannot see your hand an inch below the surface. This dark water absorbs sunlight and warms the upper layers of the bog, while the deeper layers stay cold and still. The bog creates its own quiet layers of temperature, stacked one on top of another, each one a slightly different world. The water in a bog also becomes acidic over time. The sphagnum moss releases hydrogen ions as it grows, slowly lowering the pH of the water. Most bogs have a pH between 3 and 4, which is roughly as acidic as orange juice or vinegar. Very few organisms can survive in water that acidic. The bog uses its own chemistry to keep the world simple, to limit competition, to hold the space for the slow work of preservation. preservation. Now consider where that water came from. Every drop of rain that falls into a bog began as water vapor rising from the ocean. The sun warmed the sea surface, lifted the water into the air, and wind carried it inland. That same water may have cycled through the atmosphere dozens of times before landing in this particular hollow in the ground. And the water itself, the molecule of hydrogen and oxygen that makes it up, is ancient beyond imagining. Water molecules on Earth are billions of years old. Some scientists believe a significant portion of Earth's water arrived here long ago, carried by icy comets and asteroids that struck the young planet. The water standing still in a cold, dark bog may have traveled across the solar system to get here. The oxygen in that water was forged inside stars. The hydrogen is older still, formed in the first few minutes after the universe began. Every molecule of bog water carries within it a history that stretches back almost 14 billion years. It drifted through space. It fell to a young Earth. It cycled through oceans and clouds and rained for billions of years. And now it rests here, cold and still, cradling the slow, quiet work of a bog. The bog does not rush. It does not need to. It has all the time in the world, and the water it holds has been waiting even longer. There is something deeply calming about that. The stillness of the bog is not emptiness. It is patience, ancient, unhurried, and full of purpose. Beneath the soft, spongy surface of a bog, something quiet and powerful is always at work. You can't see it. You can't hear it. But it shapes everything. The color of the water, the texture of the peat, even what lives and dies in this strange, still world. It is chemistry. And in a bog, chemistry moves like a slow tide, reshaping the land one molecule at a time. Start with the water. Bog water is not like the water in a river or a lake. It is deeply acidic. Most bogs have a pH between 3 and 4, about as acidic as vinegar or black coffee. That acidity comes almost entirely from sphagnum moss, the small, pale plant that builds the bog from the ground up. Sphagnum releases hydrogen ions into the water as it grows. Those ions push out other minerals like calcium and magnesium that most living things need to survive. The bog water becomes lean and sharp, stripped of nutrients, hostile to almost everything. This acidity does something remarkable. It slows decay almost to a stop. In a healthy forest, a fallen leaf breaks down in weeks. Bacteria and fungi get to work fast. They pull the leaf apart, recycle its nutrients back into the soil. But in a bog, those same bacteria and fungi struggle to survive. The acid water is too harsh. The cold temperatures slow them further. And sphagnum moss adds one more weapon. It releases a compound called sphagnum, a natural preservative that binds to the enzymes bacteria used to break down organic matter. Without those enzymes, the bacteria simply cannot do their job. Dead plants pile up. Dead animals pile up. Nothing rots. Everything accumulates. This is why peat exists at all. Peat is the slow, compressed result of thousands of years of things not rotting. Each layer is a record of what grew and died in that spot, sealed in place by acid and cold and the quiet chemistry of moss. The darkness of bog water tells its own story. That deep amber color, like strong tea held up to the light, comes from tannins and humic acids leaching out of the decaying plant matter. These compounds dissolve into the water and stain it that rich, warm brown. They also absorb ultraviolet light, the kind of radiation that can damage living cells. Bog water filters out UV rays so efficiently that the deeper you go, the darker and more still the water becomes. Light fades, life thins. The chemistry of the bog creates its own kind of shadow. Oxygen plays a role too, or rather, the absence of it. Below the surface of a bog, the waterlogged peat contains almost no oxygen. This is called an anaerobic environment, meaning one without air. Most of the microbes that break down organic matter need oxygen to survive. Without it, they cannot function. The bog becomes a place where the normal rules of decomposition simply do not apply. Things that fall in are held, preserved, kept. This lack of oxygen also drives a quieter chemical process. In the deepest, oldest layers of peat, microbes that don't need oxygen at all, called anaerobic bacteria, slowly release methane gas as they break down organic matter. Methane is a powerful greenhouse gas, one that traps heat in the atmosphere far more efficiently than carbon dioxide over a short period of time. Bogs naturally release small amounts of methane as part of their chemistry. It is one of the ways the bog breathes, slowly and invisibly, into the sky above. Iron gives some bogs their rust-red streaks. Where iron-rich groundwater seeps into a bog, bacteria that feed on iron leave behind deposits of iron oxide, the same compound that makes rust orange. You can sometimes see it as a shimmering, oily film on the surface of bog pools, thin as a soap bubble, catching the light in pale golds and blues. It looks almost alive. In a way, it is the visible trace of bacteria doing their slow, invisible work. All of these forces, the acid, the cold, the absence of oxygen, the tannins, the methane, the iron, work together in a system of quiet precision. Each one reinforces the others. The acid slows decay. The slow decay keeps oxygen levels low. The low oxygen preserves the peat. The peat holds the water. The water feeds the moss. The moss makes more acid. Round and round it goes. A cycle that has been turning for thousands of years, long before anyone was here to notice it. The bog does not need us to understand it. It simply continues, patient and dark and perfectly arranged, doing what it has always done. Somewhere in northern Europe, a farmer's plow once struck something strange just beneath the surface of a bog. It wasn't a root. It wasn't a stone. It was a human face, perfectly preserved, staring up from the dark water as if it had only just closed its eyes. The body was over 2,000 years old. Peat bogs have kept more than a few secrets like this one. The preserving power of a bog is almost impossible to believe until you see it. The cold, acidic water inside a bog contains almost no oxygen. Bacteria need oxygen to break things down. Without it, the normal process of decay slows to nearly nothing. A body placed in a bog doesn't rot the way it would in soil or open water. Instead, it is slowly tanned, the way leather is made from animal hide. The acids in the water, mostly from sphagnum moss, its shape across centuries. More than 1,000 bog bodies have been found across northern Europe, from Ireland to Denmark to Germany. That number is almost certainly just a fraction of what remains. Most bogs have never been fully explored. Scientists believe many more bodies lie waiting, still and dark, in places no plow has ever reached. Some of these people died more than 2,000 years ago. To put that in scale, if you laid 2,000 years end to end as a single mile of road, the Roman Empire would begin about halfway along. The Egyptian pyramids would be behind you, nearly a mile back. And these bodies, resting in the bog, would have entered the water right around the middle of that road. At the moment, Julius Caesar was still alive. One of the most famous is a man found in Denmark in 1950 in a bog called Toland Fen. He is known as Toland Man. His face is so well preserved that the workers who found him thought he had died recently. They called the police. When scientists examined him, they found stubble on his chin, wrinkles on his forehead, and the peaceful expression of someone asleep. He had been in that bog for roughly 2,400 years. His last meal was a kind of porridge made from barley and seeds. Scientists could tell because his stomach contents were still intact. He had eaten about 12 to 24 hours before he died. The seeds in his stomach included plants that bloom in winter and early spring. He likely died sometime in the cold months, when the bog was still and gray and quiet. Toland Man was not alone in how he died. Many bog bodies show signs of what archaeologists call a ritual death. Some were strangled. Some were struck on the head. Some were placed in the water with care, their eyes closed, their limbs arranged gently. Scientists believe these people may have been offerings given to the bog as a gift to the earth or to the gods that ancient people believed lived in the water. The bog received them, and it kept them. This is one of the most striking things about the scale of what bogs hold. These are not fossils, hardened into stone over millions of years. These are soft tissues, real skin, real hair, real fingerprints, preserved in something not much deeper than a backyard garden pond. Toland Man's fingerprints are clear enough to take a print from. used to hang him is still intact, the fibers still flexible after 2.5 millennia. The oldest known bog body is far older still. Kolbjerg woman, found in Denmark, dates back roughly 10,000 years. She lived at the end of the last ice age, when glaciers still covered much of northern Europe, and humans were just beginning to settle into permanent communities. She is one of the oldest human remains ever found in all of Scandinavia. The bog held her through the entire rise and fall of ancient civilizations, through the invention of writing, through the building of every cathedral and city in Europe. And she was still there, waiting, when a peat cutter's spade finally found her. The bog does not rush. It does not forget. It simply holds in its cold and quiet dark everything that has been given to it. And in that stillness, it offers something remarkable back to us. A window into lives lived so long ago that no written record survives. The bog is the record. The water is the ink. And the bodies it keeps are the words of a story that would otherwise be lost forever. Imagine standing at the edge of a peat bog on a cool, gray morning. The ground beneath your feet feels soft. It gives a little with each step, like walking on a wet sponge. The surface trembles slightly, even when you stand still. That gentle trembling has a name. Scientists call it a quaking bog. And it happens because the top layer of peat floats on water beneath it. You are, in a very real sense, standing on a raft made of ancient moss and time. Look out across the surface. It isn't flat the way a field is flat. It rolls and hummocks, small mounds and hollows spread out in every direction like a slow, frozen wave. The mounds are built by sphagnum moss, that remarkable little plant that holds 10 to 20 times its own weight in water. Each mound is slightly higher than the ground around it, and between the mounds sit shallow pools of dark water. These pools are still and black, like small mirrors reflecting the pale sky above. The colors of a bog are unlike anything else in nature. The sphagnum moss comes in deep shades of rust, gold, and olive green. Some patches glow almost red in the right light, especially in autumn. Other patches are a soft, pale yellow-green, almost luminous against the dark water. surface looks like a patchwork quilt stitched together from every shade of brown, amber, and green you can imagine. It's quiet and strange and deeply beautiful. The peat beneath that surface is doing something remarkable. It is storing memory. Every layer of peat holds a record of what the world looked like when that layer was alive. Scientists can drill a thin core of peat from the bog and read it like a book. Pollen grains are preserved in peat for thousands of years. Each grain is so small you need a microscope to see it, but each one carries the shape of the flower or tree that made it. By studying which pollen grains appear in which layer, scientists can reconstruct entire ancient forests, meadows, and climates that existed long before any human wrote a single word. This record is astonishingly precise. A core of peat just 1 meter long might contain 10,000 years of history. Scientists have used peat cores to track the spread of farming across ancient Europe, watching as the pollen of wild trees slowly gives way to the pollen of wheat and rye. They've found evidence of volcanic eruptions, of sudden cold snaps, of droughts that lasted centuries. The bog holds all of it, sealed in acid and water, perfectly still. The surface of the bog also holds seeds, viable seeds that can still grow, have been found in peat layers thousands of years old. The cold, acidic, oxygen-poor conditions slow down decay so completely that even fragile biological material survives. Scientists have germinated seeds recovered from bog sediments, watching plants grow that haven't existed on Earth's surface for millennia. The bog doesn't just remember. In some cases, it can bring the past back to life. Walk a little further across the surface, and you'll notice the ground changes. Near the center of a raised bog, a bog that has grown so thick it actually domes upward in the middle, higher than the land around it. The surface is wetter, more open. The pools are wider here. The moss is thicker. Raised bogs can grow to be several meters higher at their center than at their edges, built entirely by the slow accumulation of dead sphagnum over thousands of years. That dome shape is the bog's own doing, shaped by nothing but rain and growth and time. The edges of the bog are different again. Here, where the bog meets drier ground, the surface firms up. Shrubby plants take hold. Heather grows in low, dense mats, its tiny purple flowers appearing in late summer like a soft blush across the brown landscape. Stunted trees sometimes manage to survive at the margins, their roots twisted and shallow. Because the waterlogged peat offers so little oxygen, they look ancient even when they're young, bent, and gnarled by the effort of growing in a place that doesn't easily welcome them. Every part of the bog's surface tells a different story. The trembling center, the hummocks and pools, the rust-red moss, the pollen and seeds locked in the dark layers below. All of it is a record, written slowly over thousands of years, in a language made of water and carbon and quiet. The bog doesn't shout its history. It holds it gently, the way still water holds a reflection, clear and undisturbed, waiting for someone to look. Beneath the soft, spongy surface of a peat bog, something extraordinary is happening. It moves too slowly for any human eye to catch. But given enough time, the bog does something almost impossible to believe. It turns dead plants into stone. Not overnight, not in a century. Over millions of years, the compressed layers of peat can transform into coal, the same black rock that powered the Industrial Revolution, that heated homes and drove steam engines across continents, began its life as a bog very much like the ones still forming today. When you hold a piece of coal in your hand, you're holding something that was once a living plant, pressed and changed by time and heat, and the slow, enormous weight of the earth above it. The process starts with peat itself. Peat is the first stage. It's soft, dark, and still recognizable as plant material. You can sometimes see the shapes of leaves and stems inside it. But as peat gets buried deeper under new layers of sediment, the pressure builds. The temperature rises. The water gets squeezed out. Over time, peat becomes lignite, a soft brownish coal that still holds some of the original plant structure. Geologists call it brown coal, and it burns, though not as cleanly or as hot as the harder kinds. Deeper still, with more pressure and more heat, lignite becomes bituminous coal, the kind most people picture when they think of coal. It's dense and black, holds enormous amounts of stored energy. Push it even further, under even greater pressure for even longer, and it becomes anthracite, the hardest and purest form of coal. Anthracite burns the hottest of all, and it glitters with a faint metallic sheen when the light catches it just right. This whole transformation from living plant to peat to coal is called coalification. It's one of the slowest chemical changes on Earth. The coal seams we mine today formed mostly during a period called the Carboniferous, which means coal-bearing, a stretch of time roughly 300 to 360 million years ago. The world back then was covered in vast, warm swamp forests. Giant ferns grew as tall as trees. Dragonflies with wingspans wider than your arm glided through the humid air. When those plants died, they fell into shallow swamps and began the same slow process that peat bogs carry out today. Those ancient bogs were enormous. The coal deposits they left behind stretch across continents. The Appalachian coal fields in North America, the great seams beneath Wales and Yorkshire in Britain, the vast reserves under parts of Russia and China. All of them trace back to swampy, boggy forests that lived and died hundreds of millions of years before the first dinosaur walked the earth. What's remarkable is that the carbon those ancient plants pulled from the air is still locked inside the coal. When we burn coal, we're releasing carbon that was captured from the atmosphere during the Carboniferous period. We're undoing, in a matter of seconds, what took millions of years to store. The bog is patient. It holds things, but it can only hold them if we let it. Modern peat bogs are not old enough to become coal. Not yet. They're still in the very first stage of that long process. The peat forming in Ireland or Siberia or Canada right now won't become coal for hundreds of millions of years if the conditions are ever right. But they're already doing the same work. They're pulling carbon from the air. They're compressing plant matter. They're building layers, one slow millimeter at a time. Scientists have found something fascinating when they drill down through peat and into the layers beneath. The deeper you go, the denser and darker the material becomes. Near the surface, the peat is light and fibrous, almost like a sponge. A meter down, it's darker and more compressed, several meters down, it starts to feel almost like soft earth. The transition is gradual, but it's real. You can hold a core sample, a long cylinder of material pulled straight up from the bog, and read the history of thousands of years in its layers, like rings in a tree. Each layer holds a record: pollen grains, tiny seeds, the remains of insects, even traces of ancient volcanic ash from eruptions that happened on the other side of the world. The bog doesn't just store carbon, it stores time itself, pressed and preserved in the dark, waiting quietly beneath the surface of a place that, from above, might look like nothing more than a muddy field. The earth keeps its oldest secrets in the places that seem the most ordinary. The bog does not look like a garden at first. It looks like a place where growing things have given up. The ground is wet and cold. The water is dark. The soil holds almost no nutrients, none of the rich minerals that most plants need to survive. And yet, life is here. Strange life, patient life, plants that have learned to live by different rules. Sphagnum moss is the foundation of everything. It grows in thick, soft mats across the surface of the bog, soaking up water like a living sponge. But sphagnum does something remarkable as it grows. It releases acids into the water around it, making the bog more and more hostile to other plants. In doing so, it clears the space for a very specific community of plants, ones that can handle cold, acid, waterlogged ground. The bog is not random. It is carefully shaped, year by year, by the plants themselves. Cotton grass is one of the first things you notice when you walk near a bog in summer. It grows in tall, thin stalks, and at the top of each one sits a soft white tuft that catches the wind. From a distance, a bog full of cotton grass looks like it's dusted with snow. The white tufts are actually the plant's seed heads, and the wind carries those seeds across the open bog. Cotton grass loves the wet, nutrient-poor ground that most plants avoid. It has found a way to thrive in exactly the conditions that push everything else away. Heather is another constant presence. It grows low and dense across the surface of many bogs, especially in Scotland and Northern Europe. In late summer, Heather blooms in waves of purple and pink, and the bog transforms. The color spreads across the ground in every direction. Heather is tough. It can survive cold winters, poor soil, and long dry spells. It has a shallow root system that spreads wide rather than deep, pulling what little it needs from the thin layer of living peat near the surface. Bog rosemary grows here too, though it is not related to the rosemary you find in a kitchen. It is a small, low shrub with pale pink flowers and narrow leaves. The leaves have a waxy coating that helps the plant hold onto moisture even when the air is dry. This is one of the bog's quiet rhythms. Every plant here has found a specific way to manage water, nutrients, and cold. Each one fits into the system like a piece of a puzzle. Cranberries are native to bogs. The wild cranberry plant is a low, creeping vine that spreads across the sphagnum surface. Its small, round berries ripen in autumn, turning from white to deep red as the season cools. Indigenous peoples across North America harvested wild cranberries from bogs for thousands of years, using them for food and medicine. Today, commercial cranberry farms flood their fields with water to harvest the berries, a method that mimics the bog's own flooded surface. Bog asphodel grows in the wetter parts of European bogs, sending up spikes of small yellow flowers in midsummer. After the flowers fade, the seed pods turn a deep orange, and the plant glows against the dark water. There is a rhythm to this. Spring brings new growth pushing up through the moss. Summer brings flowers and color. Autumn brings seeds and dying stems. Winter strips the surface bare. Then the cycle begins again, slowly, quietly, over and over. What makes the bog's plant community so unusual is how tightly it is controlled by chemistry. The acid in the water, the lack of nutrients, the constant saturation, these forces act like a filter. They block most plants from entering. Only the ones with very specific adaptations can survive. This means that bogs around the world, even ones separated by thousands of miles, often contain many of the same plant species. A bog in Ireland and a bog in Canada can look remarkably similar because the same harsh conditions have selected for the same solutions. The plants of the bog are not just surviving. They are shaping the bog itself. Their dead leaves and stems fall into the water and become part of the peat. Their roots hold the surface together. Their acids keep the water chemistry stable. Each plant is both a product of the bog and a builder of it. The bog grows because the plants grow. The plants grow because the bog exists. It is a slow, ancient loop, turning over centuries, building depth and darkness, one thin layer at a time. The bog does not exist alone. It sits inside a wider world, and that world presses in from every side. At the edges, where the wet ground slowly gives way to drier soil, a whole community of creatures has learned to live right on the border. Some visit, some hunt, some have found a way to eat the bog itself in their own quiet fashion. Dragonflies are among the most ancient hunters in the bog. They have been flying over wetlands for more than 300 million years, long before the first dinosaurs walked the earth. A dragonfly can spot movement with its enormous compound eyes, which cover most of its head and give it nearly 360-degree vision. It catches prey in midair, using its legs like a basket to scoop up smaller insects. On a warm bog morning, you might see dozens of them hovering just above the water, their wings catching the light like thin pieces of glass. Frogs and toads gather at the bog's wet edges to lay their eggs in spring. The still, shallow water is perfect for raising young. Tadpoles feed on algae and tiny particles floating in the dark water. As they grow, they move to the drier ground nearby, where they hunt insects in the moss and heather. The bog feeds them at every stage of their lives, and in return, they feed the birds and snakes that live nearby. Nothing here is wasted. Carnivorous plants, the ones that trap and digest insects, are some of the most remarkable living things on Earth. They evolved in bogs because bog soil is so poor in nutrients, especially nitrogen, that ordinary plants struggle to survive. These plants found a different way. They get their nitrogen not from the soil, but from the bodies of insects. The sundew, a small plant with sticky red hairs on its leaves, is one of the most common. Each hair is tipped with a glistening drop of mucus that looks exactly like morning dew. An insect land miles around it over the course of several hours. The plant then releases digestive fluids and absorbs the nutrients directly. The Venus flytrap is the most famous of these plants, but it actually grows only in a very small region of North and South Carolina in the United States. It is not a bog plant in the strictest sense, but it grows in the same kind of wet, nutrient-poor, acidic soil. Its leaves snap shut in under a second when an insect touches the tiny trigger hairs inside. Scientists have found that the trap only closes if those hairs are touched twice within about 20 seconds. This prevents the plant from wasting energy snapping shut on a raindrop or a falling leaf. The bladderwort is perhaps the most surprising of all. It lives entirely underwater, floating in bog pools. It has no roots. Instead, it grows tiny bladders, each one smaller than a grain of rice, along its stems. Each bladder is a trap. It holds a vacuum inside, and when a water flea or a tiny larva brushes against the trigger hairs at the entrance, the bladder snaps open and sucks the creature inside in less than a millisecond. It is one of the fastest movements in the entire plant kingdom. Birds are drawn to the bog in great numbers. Curlews, with their long curved bills, probe the soft moss for worms and grubs. Hen harriers, low-flying hawks with pale gray wings, sweep across the open bog surface, hunting for small mammals and birds. In northern bogs, golden plovers nest directly on the ground among the heather, their brown-speckled feathers making them almost invisible. The bog offers them open sightlines in every direction, so they can spot danger from far away. Otters sometimes travel through bogs along stream channels, hunting for fish and frogs. Their dense, waterproof fur keeps them warm even in the cold, dark bog water. Red deer graze at the bog's edge in the early morning, moving quietly through the mist. Their hooves press into the soft peat, leaving deep prints that fill slowly with brown water. Every creature here has found its place inside a system that runs on scarcity. The soil is poor. The water is cold and acidic. Nutrients are hard to find. And yet, life has answered every one of those challenges with something extraordinary. A plant that eats insects. A bird whose feathers match the moss. this same kind of place since before the continents took their current shape. The bog rewards patience. It always has. The bog looks empty at first. Stand at its edge, and you might see only flat, wet ground stretching toward the tree line. But look closer. Something moves in the cotton grass. Something ripples the dark water near the sedge. The bog is full of life, and some of that life is extraordinary. The bog skater is one of the strangest insects in the world. It walks on water, not as a trick, but as a way of life. Its legs are coated in tiny, water-repelling hairs that spread its weight so evenly across the surface that it never breaks through. These insects hunt on the film of the water itself, feeling for the tiny vibrations of struggling prey. The surface of the bog pool is their entire world, above and below at once. Dragonflies have been hunting over wetlands for more than 300 million years. They were here before the dinosaurs. The species alive today are nearly identical to fossils found in ancient rock. The bog has not changed them much because they were already perfect. A dragonfly can fly in any direction, forward, backward, sideways, even hover in place. It catches up to 95% of the prey it chases. No other hunter on Earth, in the air or on land, comes close to that success rate. The bog also shelters creatures that most people never think about. The large heath butterfly lives almost nowhere else. It needs the open, wet expanse of a raised bog to survive. Its caterpillars feed on cotton grass, and its wings are the pale, dusty color of a cloudy sky. As bogs have been drained and destroyed across Europe, this butterfly has vanished from huge areas where it once flew. In Britain, it is now found in only a fraction of the places it once lived. The bog is not just its home. It is the only home it has. Some bogs in the far north are home to the Siberian crane, one of the rarest birds on Earth. Fewer than 4,000 of them remain in the wild. These birds travel thousands of miles each year from their breeding grounds in the Siberian wetlands to their wintering spots in Asia. Their nesting sites sit in remote, boggy tundra, the kind of cold, wet, open ground that most animals avoid. The crane depends on that isolation needs the bog's emptiness to raise its young safely. Beneath the water, the bog hides another world entirely. Bog pools are home to rare species of water beetles that exist in only a handful of places on Earth. Some of these beetles have not changed in millions of years. They breathe by trapping a bubble of air under their wing covers and diving down into the dark water to hunt. They are small, but they are ancient. They carry the whole history of their species in their bodies. The adder is the only venomous snake native to Britain, and it loves the bog. It basks on hummocks of sphagnum moss in the early morning sun, soaking up warmth before the day cools. The bog gives it shelter, hunting ground, and the kind of undisturbed quiet that snakes need. Adders are not aggressive. They move away from people when they can. But in the bog, they are at home in a way they rarely are anywhere else. Perhaps the most surprising bog animal is the carnivorous sundew's neighbor in the food chain, the crane fly. Crane flies lay their eggs in the wet peat, and their larvae, called leather jackets, because of their tough, gray skin, live underground in the bog for months. They are eaten by everything. Golden plovers probe the soft peat for them. Frogs snap them up at the surface. Even some of the bog's carnivorous plants trap adult crane flies in their sticky leaves. The crane fly is the bog's great connector, feeding layer after layer of the food web. What ties all these animals together is the bog's strange gift of extremes. It is too acidic for most creatures, too wet, too cold in winter, too exposed in summer. The animals that live here have solved problems that most species never face. They have found ways to breathe in dark water, to walk on its surface, to nest in its frozen edges, to eat what nothing else will touch. The bog does not make life easy, but the creatures that stay have become something remarkable. They are shaped by this place, and in return, they keep it alive, moving its energy from plant to insect to bird to sky. Every wing beat over the dark water is part of something much larger than itself. Peat bogs make their own weather. That sounds like something from a fairy tale, but it's true. A large, healthy bog can generate its own fog, hold its own moisture, and change the air directly above it in qualities that set it apart from every field and forest around it. Here is how it works. Sphagnum moss, that soft, spongy plant that builds the bog from the ground up, holds an enormous amount of water. A single handful of living sphagnum can hold 20 times its own weight in water. All of that moisture has to go somewhere. On cool mornings, it rises. It lifts off the surface of the bog as a thin, pale mist, curling upward in slow spirals. If you stood at the edge of a bog at dawn, you would see this fog hanging low over the water and moss, catching the first pale light of the sun. It looks like the bog is breathing. This mist is not just beautiful. It does real work. It keeps the air above the bog cool and wet. It slows the movement of wind across the surface. It creates a thin envelope of humid air that sits over the bog like a blanket. Scientists call this a microclimate, a small, local weather system that exists only in one specific place. The bog's microclimate is cooler and wetter than the land around it, sometimes by several degrees. That difference matters enormously. The plants and animals of the bog depend on that coolness. Sphagnum moss cannot survive in warm, dry air. The moment the microclimate breaks down, if the bog is drained or damaged, the moss begins to die. And when the moss dies, the whole system starts to unravel. Rain plays a special role in the bog's world. Most wetlands receive water from rivers, streams, or groundwater flowing in from nearby land. But a raised bog, the dome-shaped kind that grows up over thousands of years, receives almost all of its water from rain alone. Scientists call this type of bog ambrotrophic, which means fed by rain. The word comes from the Greek for cloud. A raised bog lives entirely on what falls from the sky. This makes the bog exquisitely sensitive to rainfall patterns. A long, dry summer can stress the surface layers of a bog. A wet year can help it grow. Over centuries, the layers of peat that build up inside a bog carry a record of every drought and every flood. Scientists can read those layers like a diary. They find dark, dense peat from dry periods and lighter, fluffier peat from wet ones. The bog remembers the rain. There is something else the fog and moisture do that most most people never think about. They trap heat at night. On a clear night, open land loses heat quickly. The ground cools fast, but a bog, wrapped in its own humid air, holds warmth longer. The water in the moss and the moisture in the air above it act as a kind of slow-release heat store. The bog stays slightly warmer than the surrounding land through the coldest hours before dawn. This small difference can protect the most delicate bog plants from frost damage on nights when nearby fields turn white and brittle. The surface of a bog also changes color with the weather. On a gray, overcast day, the sphagnum looks deep green and almost blue in the shadows. After rain, it brightens to an almost electric lime. In dry spells, the top layer bleaches to a pale, dusty white. The bog shifts and changes its appearance with every shift in the sky above it. It is one of the most responsive surfaces in the natural world. Even the way sound travels across a bog is different. The soft, wet moss absorbs sound rather than reflecting it. A bog is quiet in a way that feels almost physical. The sounds that do carry a bird call, the drip of water from a sedge leaf, the faint hiss of wind across cotton grass, seem clearer and more distinct because there is so little background noise to compete with them. The bog holds silence the way it holds water, carefully, completely. All of this, the fog, the rain, the microclimate, the changing colors, the deep quiet, adds up to something rare. A bog is not just a place where unusual things live. It is a place that actively shapes the world immediately around it. It reaches up into the air above it and changes what is there. It pulls moisture from clouds and holds it close. It breathes out mist in the morning and draws heat in at night. The bog tends to itself, quietly and without pause, the way it always has. Far to the north, where the sky stays pale for months at a time, the bogs take on a different shape. The ground there doesn't just hold water, it freezes. And in that freezing, it becomes something stranger and more powerful than anyone first expected. These are the permafrost bogs. Permafrost is ground that stays frozen all year long, even in summer. It sits just below the surface like a hidden floor of ice, sometimes stretching hundreds of feet down into the earth. far north of Russia, Canada, and Scandinavia. This frozen ground holds some of the largest peat deposits on the planet. For a long time, the people who lived near these bogs understood them in practical ways. The Nenets people of Siberia, the Sami of northern Scandinavia, and the indigenous peoples of northern Canada all knew these landscapes well. They read the ground the way others read maps. They knew which patches of bog were safe to cross and which would swallow a sled whole. That knowledge was passed down through generations, quiet and careful, long before any scientist arrived with instruments. Western explorers came later. In the 18th and 19th centuries, expeditions pushed into the far north looking for trade routes, new land, and resources. What they found instead were vast stretches of ground that behaved in ways they didn't understand. The land seemed solid in winter, then turned soft and treacherous in the brief summer thaw. Whole sections of ground would bubble and shift. Strange mounds rose from flat plains. The explorers wrote about these things with confusion. They didn't yet have the words for what they were seeing. Those mounds had a name that came later: pingos. A pingo is a hill made of ice, pushed up from below by freezing water under pressure. They can grow as tall as a 7-story building. Some pingos take hundreds of years to form. When they collapse, they leave behind round lakes called pingo scars. And those scars slowly fill with water and begin to grow into bogs of their own. The land is always changing, always beginning again. Scientists began to study permafrost more seriously in the 20th century, especially after World War II. Engineers building roads and pipelines in Alaska and Siberia kept running into a problem. Their structures would sink, foundations cracked, roads buckled. The frozen ground, disturbed by heat from buildings and engines, would thaw just enough to lose its strength. That was when engineers and geologists started to understand how much of the North was built on ice. Roughly a quarter of the land in the northern hemisphere sits on permafrost. That number surprised almost everyone. Russian scientists were among the first to map these regions in detail. Soviet-era expeditions traveled deep into Siberia, drilling cores from the frozen ground and measuring temperatures at different depths. What they found was a record of climate stretching back tens of thousands of years, locked inside the ice and peat. The permafrost had been keeping secrets. It held frozen plants, frozen insects, and frozen animals, all preserved with quiet precision. One of the most famous discoveries came in 1977 when gold miners in Siberia uncovered a baby mammoth frozen in the permafrost. She was named Dima. Her skin, hair, and organs were still intact after roughly 40,000 years. She was not alone. Over the decades, Siberia gave up more frozen animals: woolly rhinoceroses, ancient horses, cave lion cubs, and even tiny worms that scientists coaxed back to life after being frozen for tens of thousands of years. The bog and the permafrost together had acted as a natural deep freeze, holding the past in place while the rest of the world moved on. What the scientists slowly pieced together was something remarkable. The permafrost bogs of the north were not just cold versions of the bogs further south. They were a different kind of archive, where a temperate bog in Ireland might hold a few thousand years of pollen and plant material. A Siberian permafrost bog could hold records going back to the last ice age. Each layer told a story about temperature, rainfall, and the kinds of plants that grew in that era. Reading those layers was like reading a very long, very slow book about the history of the Earth's climate. The discovery of these frozen bogs changed how scientists thought about the planet's past. And slowly, as the 20th century gave way to the 21st, it began to change how they thought about the planet's future. The ice that had kept all those secrets safe for so long was starting, in some places, to melt. What had been frozen for millennia was beginning to wake up. Peat bogs look wet. They feel wet. They smell wet. So the last thing you'd expect is fire. And yet, peat burns. It burns slowly, deeply, and for an extraordinarily long time. A peat fire doesn't race across the surface the way a forest fire does. It creeps downward into the earth itself, eating through layers of compressed plant matter that took thousands of years to form. Scientists call these smoldering fires, fires that burn without a flame. through sand. Quiet, patient, relentless. This happens because dry peat is, at its core, fuel. It's made of carbon-rich plant material that never fully broke down. When the surface of a bog dries out during a drought, or after humans drain the land nearby, that ancient stored energy becomes available. A single spark, a lightning strike, even the slow heat of a dry summer can start a fire that travels underground for months, sometimes for years. These underground fires are called zombie fires. That name is informal, but scientists use it too, because it captures something true about them. A zombie fire can go dormant through a cold winter, buried under snow, appearing to be completely out. Then, when spring arrives and the ground warms again, the fire wakes up and keeps burning right where it left off. Researchers have documented fires in Siberia and Canada that smoldered underground through entire winters and reignited in the same spot the following summer. The fire never died. It simply waited. The smoke from a peat fire carries something unusual because the material burning is so old and so dense. Peat smoke contains high concentrations of carbon monoxide and fine particles, tiny bits of matter, so small they travel deep into human lungs. Large peat fires can push this smoke across entire countries. In 2015, fires burning through the peatlands of Indonesia sent a thick, choking haze across Southeast Asia for months. Scientists estimated those fires released as much carbon into the atmosphere as the entire annual emissions of Germany. All of it from ground that was supposed to be a wetland. What makes this even stranger is that peat fires can burn underwater. Not literally beneath a river, but beneath the waterlogged surface of a bog that still appears wet. If the fire reaches a layer of peat that's dry enough, even a few inches below standing water, it can continue to burn. The water above doesn't always stop it. This is one of the reasons peat fires are so difficult to extinguish. You can pour water on the surface, and the fire simply moves deeper or sideways, finding the next dry seam of ancient carbon. Firefighters who work peat fires describe the ground as unpredictable. A person can walk across what looks like solid, damp earth suddenly break through into a hollow space where the peat beneath has already burned away. The surface holds its shape even after the material below is gone, like a thin crust over empty air. In some fires, these hollow pockets extend several feet down. The ground becomes a kind of shell. There's a strange irony here that scientists find genuinely striking. Peat bogs exist because they are wet. The waterlogged conditions are what stopped the plant material from decaying in the first place. That same preserved carbon, locked away safely for millennia, becomes a source of enormous atmospheric damage the moment the water disappears. The very thing that made the bog a carbon vault is the same thing that makes it dangerous when it dries. Remove the water, and thousands of years of stored carbon can release in a single season. Peat fires also change the land permanently in ways that other fires don't. A forest fire burns the surface and leaves the soil mostly intact. A peat fire burns the soil itself. After a deep peat fire moves through an area, the ground is physically lower. The land subsides, it sinks. Because the material that once filled that space is simply gone. In some parts of Indonesia, land that burned through repeated peat fires has sunk low enough to flood permanently during high tides. The fire didn't just burn the bog, it erased it. And still, in places where humans haven't disturbed the water table, where the sphagnum moss keeps the surface soaked and the peat stays saturated, the bog holds its fire at bay. The water does its quiet work. The carbon stays locked. The ancient layers keep building, one slow millimeter at a time, the way they always have. For thousands of years, people have pulled peat from the ground and burned it. The smoke rose in thin gray columns above the moors. The warmth spread through stone cottages and small rooms, and the bog slowly gave up what it had spent centuries building. Peat burns. That simple fact changed the lives of millions of people across Ireland, Scotland, Scandinavia, and Russia. In places where trees were scarce, peat was the only fuel available. Families cut it by hand in long, dark bricks, stacked it to dry in the open air, and carried it home before winter arrived. The smell of burning peat is thick and earthy, almost sweet. People people who grew up with it say no other fire smells quite like it. Cutting peat by hand is slow, hard work. A tool called a slane, which looks like a flat spade with a small wing on one side, slices cleanly through the dense brown layers. Each cut reveals the compressed remains of plants that lived and died centuries before anyone now alive was born. A single brick of peat might hold the carbon of plants that grew 1,000 years ago. When it burns, that ancient carbon enters the air in minutes. Ireland holds some of the world's most famous peat bogs. At one point, bog covered roughly 1/6 of the entire island. For generations, Irish families depended on peat, which they called turf, for nearly all their home heating. The tradition ran so deep that the right to cut peat on a particular stretch of bog was passed down through families like land itself. A family's bog was a serious thing. It fed the fire that kept children warm through long Atlantic winters. In Finland and Russia, peat was used on an even larger scale. Finland once generated a significant portion of its electricity by burning peat in large power stations. Russia sits on some of the deepest peat deposits on Earth, and for much of the 20th century, those deposits powered factories and heated cities. The bog that had quietly stored carbon for millennia was suddenly being opened up and burned at an industrial pace. This is where the connections become striking. The sun falls on ancient wetlands. Plants grow. They die and sink. The bog holds them. Thousands of years pass. Then a person with a spade, or later a machine, opens the ground. The energy that the sun delivered to those plants long ago is released as heat and light. The bog is, in a way, a very slow battery. It charges over centuries and discharges in an afternoon fire. Burning peat also connects the bog to the atmosphere in a direct and powerful way. Peat holds more carbon per square meter than almost any other ecosystem on Earth. When it burns, that carbon becomes carbon dioxide, the gas that traps heat in the atmosphere. Scientists estimate that the world's peat bogs store roughly twice as much carbon as all the world's forests combined. Every brick of peat burned in a cottage fireplace was a small withdrawal from that vast, ancient store. Smoke from peat fires also carried something else. Fine particles drifted across fields and settled on lakes. Researchers have found layers of soot in lake sediments that match periods of heavy peat cutting in the surrounding region. The bog's history of burning is written in the mud at the bottom of nearby water. Everything records everything. Nothing disappears without leaving a mark somewhere. Even the whiskey made in Scotland carries the bog's signature. In certain Scottish distilleries, peat smoke is used to dry barley before it becomes malt. The smoke soaks into the grain. It stays there through the whole process of fermentation and distilling. The final whiskey tastes of the bog, of rain and dark earth and ancient plants. People drink it and taste something they cannot quite name. Something old and smoky and wild. They are tasting the bog without knowing it. What is remarkable is how many systems the bog touches through the simple act of burning. It touches the air. It touches the climate. It touches the water in nearby lakes. It touches the food and drink people make. It connects the deep past to the living present in the most direct way possible. A fire in a hearth in a stone cottage on a rainy Irish evening is also a conversation between the present and 1,000 years of accumulated life. The bog gave freely for a long time. People were grateful for the warmth. They did not yet know what the giving cost or how long it had taken to build what they were burning. That understanding came later, slowly, the way most important things do. Beneath the quiet surface of a bog, something remarkable is happening. Something that has been happening for thousands of years, without pause, without fanfare. The bog is breathing, and with every slow breath, it pulls carbon out of the air and locks it deep into the earth. Carbon is everywhere. It moves through the air as carbon dioxide, the gas that plants absorb when they grow. When a plant dies in most places, it decays. Bacteria break it down. The carbon inside it escapes back into the air. The cycle continues. But in a bog, that cycle stops. The cold, acidic, waterlogged conditions slow decay almost to nothing. The dead sphagnum moss sinks. The carbon stays. Year after year, century after century, the bog holds on. Scientists call this carbon storage, and peat bogs are among the most powerful carbon stores on the planet. The world's peatlands cover only about 3% of Earth's land surface. That sounds small, but they hold roughly twice as much carbon as all the world's forests combined. Every tree, every jungle, every ancient rainforest, peat bogs store more carbon than all of them put together. That number is staggering when you sit with it quietly. The carbon locked inside peat bogs has been accumulating for a very long time. Some of the oldest peat deposits began forming more than 10,000 years ago, just after the last ice age ended. The glaciers pulled back, water pooled, sphagnum moved in, and the slow, patient work of carbon storage began. Layer by layer, millimeter by millimeter, the bog built its vault. A single meter of peat can represent 1,000 years of growth. Some bogs are 10 meters deep or more. This makes the bog a kind of time capsule for the atmosphere itself. Scientists can drill down into peat and read the ancient air. Tiny pollen grains trapped in the layers tell the story of what forests grew nearby. Ash from distant volcanoes marks specific years. Even the chemistry of the peat itself reflects the climate of the past. The bog remembers what the sky was like long before humans were keeping records. But the bog is not just a record of the past. It is also a living part of the present. Right now, healthy peat bogs are still pulling carbon from the air. Sphagnum is still growing. Dead moss is still sinking. The vault is still being filled. Scientists estimate that peatlands absorb around 370 million tons of carbon each year across the globe. That is a quiet, invisible force working in the world's wettest, coldest corners, keeping the atmosphere in balance. The problem is that the vault has a weakness. It only holds when the water stays. Peat needs to stay wet to stay stable. When a bog dries out, the chemistry changes. Oxygen gets in. Bacteria wake up. The ancient carbon that took thousands of years to store begins to decay. And when peat decays, it releases carbon dioxide back into the air. The vault opens. The slow work of millennia begins to unravel. This is happening right now in many parts of the world. Bogs that have been drained for farming or cut for fuel releasing their stored carbon. Scientists estimate that degraded peatlands, bogs, that have been damaged or drained now release nearly 2 billion tons of carbon dioxide every year. That is a significant amount. It is roughly the same as the total annual emissions of all the cars and trucks in the United States. The scale of that shift is hard to picture. Imagine 10,000 years of careful storage, slowly leaking away. The bog spent centuries building something extraordinary, and the loss of it happens much faster than the building ever did. There is something deeply humbling about this. The bog did not ask for anything. It simply did what it has always done: absorbed, held, preserved. It asked for nothing but water and cold and time. For thousands of years, it quietly balanced something enormous: the carbon in the atmosphere, the warmth of the planet, the conditions that allow life to exist as we know it. The bog and the sky are in conversation. They always have been. The moss pulls carbon down. The air gives it up. The peat holds it close. When that conversation is interrupted, both sides feel it. The atmosphere warms a little more. The ice retreats a little further. The bog dries a little faster. Each change feeds the next. The earth is always moving, always adjusting. And the bog, patient and still on the surface, is one of the quiet forces keeping that movement in balance. When a bog drains, the first thing that changes is the light. For thousands of years, a living bog holds water close. The surface stays wet and dark, like a mirror that has forgotten how to reflect. Sphagnum moss drinks the rain and holds it tight. The whole system breathes slowly, quietly, in a kind of balance that took centuries to build. Then someone digs a ditch. The water moves, and everything the bog was begins to come apart. The change is visible from above. Satellites have captured it clearly. A healthy bog scene from space looks dark and rich, almost black in places, with patches of deep green and amber where the moss grows thick. There is a softness to it, a blurred edge where the wet ground meets the sky. A drained bog looks different. The color shifts. Browns and grays replace the green. The surface dries and cracks. Scientists who study land from space can spot a drained bog the way a doctor change in light is just as striking. A living bog has a particular glow in the morning. The standing water catches the sun and throws it back in small, bright pieces. The moss, still wet with dew, shines a pale gold. Dragonflies move through the low mist. The whole place hums with a quiet kind of life. When the water is gone, that glow disappears. The surface goes dull. The moss dries to a pale, brittle brown. The light no longer bounces. It just falls flat and stays there. But the loss of light is only the beginning of what the world loses. Peat, when it dries out, begins to break down. The carbon that the bog locked away over thousands of years starts to escape. It rises into the air as carbon dioxide, the gas that traps heat in our atmosphere. Scientists estimate that drained and degraded peatlands release roughly 2 billion tons of carbon dioxide into the atmosphere every single year. That number is hard to hold in your mind. It equals about 5% of all human-caused greenhouse gas emissions on Earth. A system that spent millennia pulling carbon out of the air begins, almost overnight, to push it back in. The land itself shrinks. Peat is mostly water and organic matter. When the water drains away, the peat compresses and oxidizes, meaning it reacts with oxygen in the air and slowly burns away at a chemical level. In some parts of the world, drained peatlands have sunk by several meters over just a few decades. In the Netherlands, large areas of land now sit below sea level because the peat beneath them has been draining and compressing for hundreds of years. The ground is literally disappearing. The plants go quiet too. Sundews and bog rosemary and the pale tufts of cotton grass all need that particular wet, acidic world to survive. When the water drops, other plants move in. Grasses and shrubs that prefer drier ground take over. The rare species, the ones that evolved over millions of years to live in exactly this kind of place, have nowhere else to go. They simply vanish from that spot. Some of them vanish entirely. The animals follow the plants. The specialized insects, the rare amphibians, the birds that nest in the open, wet ground, all of them depend on conditions that only a living bog provides. The large heath butterfly, for example, lives almost entirely on boggy moorland in northern Europe. As those bogs drain and dry, the butterfly's world shrinks. Its range has already contracted sharply. It is one of many species whose fate is tied directly to the fate of the water beneath their feet. And then there is the deeper loss, the kind that cannot be measured in tons of carbon or species counts. A bog that took 10,000 years to form cannot be replaced in a human lifetime. The layers of peat, each one a record of a different century, are gone once the land is plowed or built upon. The bog bodies, those extraordinary preserved figures that tell us who lived and died in ancient times, are lost forever when the peat dries and decays. The chemical darkness that kept them safe for millennia simply stops working the moment the water leaves. Light, in the end, is what reveals this loss most clearly. The dull brown of a drained field where dark, wet moss once grew. The flat, gray sky reflected in cracked earth instead of still water. The absence of that quiet morning glow. The bog does not disappear all at once. It fades slowly, like a light being turned down very, very low. When a bog is drained, something goes quiet. The soft give of wet moss underfoot disappears. The dark mirror of standing water vanishes. The whole place hardens and shrinks, and a silence settles in that feels less like peace and more like absence. But when people bring the water back, the bog begins to speak again. Restoration starts with a simple act. Workers plug the ditches that were dug to drain the land. These plugs are often made of peat itself, cut into dense blocks and pressed into the channels like corks in a bottle. The water has nowhere to go. It pools, it spreads, it rises slowly through the soil, and the bog begins to breathe again. The first sound you notice is water. Not rushing water, not the bright chatter of a stream, but something slower and lower. A soft gurgling where the channels fill, a gentle lapping at the edges of new pools. Rain falls on a restored bog, and you can hear it land differently than it does on dry ground. It hits the wet moss with a soft, dense thud, absorbed almost instantly. The way sound is swallowed by a heavy curtain. Sphagnum moss, that small and ancient builder, returns quickly once the water comes back. As it grows, it holds moisture in tiny cells within each leaf. When you press a handful of living sphagnum, it releases water like a sponge. That process, happening across millions of plants over acres of recovering bog, creates a constant, barely audible movement. Scientists describe it as a kind of collective breathing, the land itself expanding and contracting with the seasons. As the water table rises, gases trapped in the peat begin to shift. Methane, formed by the slow breakdown of old plant matter deep in the bog, moves upward through the saturated layers. It reaches the surface in small bubbles. Walk across a recovering bog, and you may hear them pop softly beneath your feet, one after another. A quiet percussion rising from the ground. It is the sound of chemistry, of ancient carbon finding its way back to the surface after centuries underground. Birds return, and they bring their voices with them. Curlews, those long-billed wading birds with their haunting, rising calls, are among the first to come back to restored bogs in northern Europe and the British Isles. Their cry carries across open, wet ground in a way it cannot carry across dry heath or farmland. The bog amplifies it, reflects it off the flat water, sends it out in all directions. Conservationists working on restoration projects often say that hearing the curlew return is the clearest sign the land is healing. Frogs and toads move in as standing water returns. Their calls in spring are low and constant, a steady hum that rises from the pools at dusk. Dragonflies follow, hovering and darting above the new water surfaces with a dry, papery flutter of wings. The bog, which had gone silent, fills back up with layered sound, each species adding its own thread to the whole. Restoration is not instant. A bog that took thousands of years to form cannot be rebuilt in a decade. But the recovery is measurable. Studies of restored bogs in Ireland, Scotland, and Scandinavia show that sphagnum cover can return within 5 to 10 years of rewetting. Carbon storage begins again within that same window. The peat stops releasing its ancient carbon into the air and starts locking it away once more. There is a sound to that process too, though no human ear can hear it directly. Researchers use sensitive instruments to measure the faint vibrations produced by microbial activity deep in the peat. The bacteria and fungi that break down organic matter create tiny pulses of movement as they work. When a bog is dry, that activity accelerates, releasing carbon fast. When the water returns, it slows. The instruments record the change as a shift in frequency, a lower, quieter signal, the bog settling back into its long, slow rhythm. That rhythm is one of the oldest on Earth. Peat bogs have been forming and storing carbon for more than 10,000 years. Since the glaciers of the last ice age retreated and left behind cold, wet hollows across the northern world, every restored bog is a small act of returning something to that ancient cycle. The water comes back, the moss grows, the birds call across the open water, the ground softens underfoot, and somewhere deep beneath the surface, in the dark and the cold and the quiet, the peat begins its slow work again, patient as it has always been, holding everything it is given. Peat bogs cover about 3% of Earth's land surface. That sounds small, but 3% of all the land on Earth is an enormous amount of ground. Scientists estimate that peat bogs store roughly 550 billion tons of carbon, more carbon than all the world's forests combined. That number is almost too large to hold in your mind. Yet it sits there quietly, locked inside dark, wet ground, waiting. Now think about the ocean. The ocean covers about 71% of Earth's surface. It is the planet's largest carbon sink, a place that absorbs and holds carbon dioxide from the air. The ocean and the atmosphere are always exchanging gases, breathing back and forth across the water's surface in a slow, ancient rhythm. Scientists have studied this exchange for decades, and what they found is that peat bogs are part of that same conversation. Here is how the numbers connect. When a bog releases carbon, it does not stay in one place. Carbon dioxide and methane drift upward into the atmosphere. The atmosphere carries them across continents and oceans. The ocean then absorbs some of that carbon at its surface. The amount the ocean can absorb depends partly on how much carbon is already in the air. So, when a bog releases its stored carbon, it shifts the balance. It changes the math that the ocean is working with. One system feeds directly into the other. Methane is the number that surprises most people. Methane is a gas that traps heat in the atmosphere about 80 times more effectively than carbon dioxide over a 20-year period. Bogs produce methane naturally. Tiny organisms deep in the waterlogged peat break down old plant matter without oxygen, and methane is what they release. A healthy, intact bog releases small, steady amounts of methane. Scientists have measured this carefully. The numbers are modest when the bog is stable. But when a bog is disturbed or drained, methane release can spike sharply. The math changes fast. There is a ratio that Earth scientists return to again and again. For every degree Celsius that global temperatures rise, permafrost bogs in the far north release measurably more carbon. The relationship is not random. It follows a curve that scientists can model and predict. The Arctic holds about half of all the world's peat. As temperatures climb, that peat thaws. As it thaws, it releases carbon. As carbon rises, temperatures climb further. Scientists call this a feedback loop, a cycle where the output becomes part of the input, turning the dial a little further each time. The numbers are elegant in a cold, precise way. They describe a system that responds to itself. The ocean feels this too. As more carbon enters the atmosphere, more dissolves into seawater. When carbon dioxide dissolves in water, it forms a weak acid. The ocean's pH, its measure of acidity, has already dropped by about 0.1 units since the industrial age began. That sounds tiny, but pH is measured on a logarithmic scale, meaning a drop of 0.1 units represents roughly a 26% increase in acidity. Coral reefs feel that change. So do the tiny shelled creatures that float near the ocean's surface. The math of the bog reaches all the way down into the sea. And yet, there is a gentler side to these numbers. An intact, healthy peat bog absorbs carbon from the air at a slow, steady rate. Over 1,000 years, a single hectare of healthy bog, an area about the size of 2.5 American football fields, can lock away hundreds of tons of carbon 4 centuries, that adds up to something vast and solid and real. The bog is patient in a way that numbers rarely capture. Scientists use satellite data now to measure bog carbon from space. Instruments aboard orbiting satellites detect the faint infrared signatures of methane rising from wetlands across Siberia, Canada, and Scandinavia. They map the numbers across thousands of miles of remote ground that no human has ever walked. The data streams down to researchers who piece together a global picture, one measurement at a time. The bog that sits silent and still beneath a gray northern sky is also, in a sense, visible from orbit. Everything connects at a scale that is hard to see from the ground. The small, dark pool of a bog in Ireland and the vast blue surface of the Pacific Ocean are running the same equation. Carbon moves between them, carried by wind and rain and the slow turning of the atmosphere. The numbers are simple. The system they describe is not. Beneath the soft, spongy surface of a peat bog, something extraordinary is sleeping. Not just moss, not just water. Entire forests lie buried down there, pressed flat and preserved by thousands of years of cold, still darkness. Trees that fell before written history. Root systems that once held the soil of ancient Europe. All of it locked away, quiet and waiting, in a layer of peat that took longer to form than most civilizations have existed. Scientists call these buried remains bogwood. When peat cutters dig deep into old bogs, they sometimes pull up logs that are perfectly intact. The wood is dark, almost black, stained by the same tannins and acids that preserve everything the bog swallows. Some of these logs come from oak trees that fell over 4,000 years ago. The grain of the wood is still visible. The rings that mark each year of growth are still there to count. Time inside a bog moves differently than it does anywhere else. This happens because of a very precise set of conditions. The bog must stay wet. It must stay cold enough to slow decay. It must stay acidic enough to stop the bacteria that would normally break organic matter down. Change any one of those 3 things, and the preservation stops. The forest stops sleeping and starts to rot. What took millennia to build can vanish unique to bogs. It shows up everywhere you look on this planet. Earth sits at just the right distance from the sun to keep liquid water on its surface. A little closer, and the oceans would boil away. A little farther, and they'd freeze solid. Scientists call this the habitable zone, the narrow band of distance from a star where temperatures allow water to stay liquid. Earth sits almost perfectly in the middle of it. The atmosphere plays its part too. That thin shell of air wrapped around the planet, mostly nitrogen and oxygen, with a small amount of carbon dioxide and other gases, acts like a soft blanket. It holds just enough heat from the sun to keep the surface warm. Without it, the average temperature on Earth would drop to around -18 degrees Celsius. Life as we know it would not exist. The bog would never have formed. The forests would never have grown in the first place. What's remarkable is how thin that blanket really is. If you shrank the Earth down to the size of an apple, the atmosphere would be thinner than the apple's skin. That's all that stands between the living world and the cold of space. And yet it works. It has worked for billions of years, through ice ages and volcanic eruptions and asteroid impacts. The system bends, but it holds. The bog is a small mirror of that same stubborn balance. Sphagnum moss keeps the water table high. The high water table keeps oxygen out. The lack of oxygen slows decay. The slow decay builds peat. The peat stores carbon. The stored carbon keeps the bog cool and stable. Every piece supports every other piece. Pull one out, and the whole structure starts to shift. Drain a bog, and the peat dries. Dry peat lets oxygen in. Oxygen wakes the bacteria. The bacteria begin to eat through thousands of years of stored material, releasing carbon dioxide back into the air. That carbon dioxide adds to the warming of the atmosphere. A warmer atmosphere dries more bogs. More dried bogs release more carbon. The cycle feeds itself quietly, without any single dramatic moment to point to. This is the fragile balance scientists worry about most. Not the sudden disasters, but the slow unraveling of systems that took ages to build. The buried forests in the bog didn't disappear overnight. They accumulated grain by grain, year by year, century by century. preservation depends on conditions staying just stable enough, just wet enough, just cold enough. And those conditions depend on the atmosphere staying just balanced enough to keep the planet in its narrow, livable range. There's something deeply calming about understanding this. Not frightening, calming, because it means the world is not held together by luck alone. It's held together by physics, by chemistry, by the slow and patient work of living systems that have been adjusting and responding for longer than we can fully imagine. The bogwood sleeping underground is proof of that patience. It has waited 4,000 years in the dark, perfectly preserved, because the conditions around it stayed true. That's not fragility. That's precision. The kind of precision that only comes from a system that has had a very long time to find its balance. There is still so much we don't know. After centuries of study, after digging into the dark layers and reading the pollen and pulling ancient bodies from the water, scientists will tell you honestly, peat bogs still hold secrets, deep ones, the kind that take generations to unravel. And somehow, that makes them even more wonderful. Start with something close to home. Scientists know that peat bogs store an enormous amount of carbon, roughly twice as much carbon as all the world's forests combined. But they don't yet fully understand how bogs will behave as the planet warms. Will they release that carbon slowly or quickly? Will some bogs adapt and keep growing while others collapse? The models are still being built. The data is still coming in. Every new study adds a piece, but the full picture isn't there yet. Some bogs are already changing in ways that surprise researchers. In parts of Siberia, the frozen ground beneath ancient bogs, called permafrost, the layer of soil that stays frozen year-round, is beginning to thaw. When it thaws, the bog doesn't just warm up. It changes shape. It sinks. It sometimes turns into a lake almost overnight, geologically speaking. Scientists call these thermokarst lakes, and they're spreading. What happens to the carbon inside them, and how fast it enters the atmosphere, is one of the most urgent open questions in climate science right now. Then there's the question of methane. Bogs produce methane, a gas that traps heat in the atmosphere as part of their natural cycle. Scientists have known this for a long which different bogs release methane, and how that rate changes with temperature and rainfall is still being measured and debated. Some bogs release far more than expected. Others release less. The reasons aren't always clear. Tiny differences in plant cover, water depth, and soil chemistry can shift the numbers dramatically. Researchers are still mapping those differences, bog by bog, season by season. Now look further out, much further. Scientists studying other planets have started asking a question that would have seemed strange not long ago. Could something like a peat bog exist somewhere else in the solar system? It sounds like a dream, but the conditions that make bogs possible, liquid water, organic material, slow decay, cold temperatures, aren't unique to Earth. They're just rare. Saturn's moon, Titan, is the most talked about example. Titan has a thick atmosphere and lakes on its surface, but those lakes aren't filled with water. They're filled with liquid methane and ethane, which are simple carbon-based compounds. Scientists have found complex organic molecules in Titan's atmosphere and on its surface. Some researchers believe that over millions of years, organic material could accumulate in certain areas of Titan, the way it does in Earth's bogs, slowly building up, layer by layer, in cold, still conditions. No one knows for certain. The chemistry would be completely different from anything on Earth, but the basic idea that carbon-rich material could pile up and be preserved in a cold, wet environment isn't impossible. Mars is another place scientists think about. Mars is dry now, but evidence suggests it had liquid water on its surface billions of years ago. Some regions may have had cold, shallow wetlands. If microbial life existed there during that wet period, could organic material have been preserved in the soil the way peat is preserved on Earth? Some scientists think it's worth looking. The Mars rovers have found organic molecules in the Martian soil, though their origin is still debated. Whether anything like a bog ever formed there, even a tiny, ancient, frozen version, remains an open question. Back on Earth, there are still bogs that have never been studied at all. Remote bogs in the Congo Basin, in the highlands of New Guinea, in the far reaches of Siberia. Many of these have been mapped from satellites never visited by scientists on the ground. Each one could hold records of climate and life going back thousands of years. Each one is a library that hasn't been opened yet, and sphagnum moss itself still surprises researchers. The exact chemical process by which it preserves organic material so perfectly is still not completely understood. Scientists know the acids involved. They know the low oxygen environment plays a role, but the precise combination of factors that can preserve a human body for 2,000 years, keeping skin and hair and even fingerprints intact. That full mechanism is still being studied. The bog keeps its secrets quietly. It doesn't rush. It has been patient for 10,000 years, and it will be patient a while longer. The scientists will keep coming with their tools and their questions, and the dark water will hold still and wait. People have always felt something strange near a bog, something old, something watching. For thousands of years, the people who lived beside these dark, still waters believed the bog was alive in a way that went beyond plants and water and mud. They were not wrong to feel that way. Across northern Europe, ancient communities left offerings at the edges of bogs. They placed weapons, tools, and jewelry into the dark water. These were not accidents. These were gifts. Archaeologists have found thousands of objects this way, carefully placed, deliberately offered. The bog was seen as a doorway between the world of the living and the world of the dead. The Celtic peoples of Ireland and Britain believed bogs sat at the boundary between realms, not just physical places, but spiritual ones. The water was neither land nor sea. The bog was neither solid nor liquid. It existed in between, and that in-between quality made it sacred. Fires were lit at bog edges during festivals. Prayers were spoken over the dark water. In Norse tradition, bogs were connected to the goddess Nerthus, a figure tied to the earth and its deep, quiet power. Ancient Roman writers described how her followers would wash her sacred cloth in a bog lake, then drown the enslaved people who had touched it, sending them into the water as offerings. The bog kept secrets. It was trusted to hold what the living world could not. The bog bodies found across Europe were not all victims of violence. Researchers believe certain individuals were chosen, honored, and placed into the bog with great care. Toland man, found in Denmark, had a calm expression on his face. His last meal was a kind of grain porridge. He was given a leather cap and a belt. Someone had taken time with him. The bog was not just a place of fear. It was a place of meaning. In Ireland, the word for bog in Irish Gaelic is moin, and it carries no fear. It carries work and warmth and home. Generations of Irish families cut peat from the same stretch of bog their grandparents had worked. The smell of burning peat became the smell of winter evenings, of bread baking, of safety. The bog was not a place apart from life. It was woven into it. Finnish folklore gave the bog its own spirit, a creature called the Suohenki, meaning bog spirit. It was said to drift through the mist on still mornings. Travelers who wandered into bogs at night were thought to be led astray by these spirits, drawn deeper into the soft ground. This was not just superstition. Bogs genuinely disorient. The flat, featureless surface offers no landmarks. The ground shifts underfoot. People did get lost. The spirit was the community's way of explaining a real danger. Now think forward, not just decades, but deep time. In 1,000,000 years, the bogs that survive today will have changed beyond recognition. The peat they hold will have compressed further, moving slowly toward the dense black carbon it has always been becoming. Some of it will have become lignite, a soft brown coal that sits halfway between peat and the hard coal buried deeper in the earth. The slow transformation continues whether or not any human is there to watch it. In 100 million years, the continents will have shifted again. Scientists believe the landmasses of Earth are moving toward a new supercontinent, sometimes called Pangea Ultima. The northern lands where most bogs exist today, Canada, Russia, Scandinavia, will have drifted into new positions. The climate will be different. The plants will be different. But somewhere in some low, wet, still place, water will collect. Sphagnum or something like it will grow. Dead matter will fall and fail to rot. A new bog will begin. In 5 billion years, the sun will expand into a red giant star, swelling outward until it swallows the inner planets. that survives will be scorched beyond anything alive today. The peat, the bog bodies, the ancient pollen records, all of it will be gone. But the carbon those bogs held, carbon that came from ancient sunlight, from ancient air, from ancient living things, that carbon will not disappear. It will scatter. It will drift. It will become part of something new. Every atom that ever passed through a bog was once a star. Every carbon molecule locked in peat was once floating in an ancient sky. The bog does not end. It transforms. And somewhere in the long future of this universe, the quiet patience of the bog, its willingness to hold, to wait, to preserve, echoes on in forms we cannot yet imagine. Close your eyes for a moment, not to sleep, not yet, just to listen. A peat bog at dawn makes almost no sound at all. There is no rushing water, no wind through tall trees, just the soft drip of dew falling from one blade of sedge grass to another. The faint, wet exhale of the earth itself. If you have ever stood in a place so quiet that you could hear your own heartbeat, a bog at first light feels something like that. But quiet is not the same as empty. Beneath that stillness, the bog is working. Sphagnum moss, that pale, spongy plant that builds the bog from the ground up, is pulling water into its tiny hollow cells right now. It does this constantly, without rest, without hurry. One small clump of sphagnum can hold up to 20 times its own weight in water. Multiply that by the billions of clumps covering a single bog, and you begin to understand how a bog becomes its own kind of sea. A sea that barely moves. A sea that breathes in slow motion. That breathing has a smell. Bogs carry a scent that is hard to describe to someone who has never stood in one. It is earthy and cool and faintly sweet, like rain on old wood. Scientists believe this smell comes partly from the breakdown of plant matter, and partly from the gases that seep up through the peat. One of those gases is methane, which forms when ancient organic material, leaves, roots, the bodies of long-dead creatures, breaks down without oxygen deep in the peat layers. The bog exhales this gas slowly, in tiny bubbles that rise through dark water and pop at the surface without a sound. In summer, the bog finds its voice, dragonflies appear first, their wings catching light like thin sheets of glass. They have lived in bogs for over 300 million years, long before the first dinosaur walked the earth. They hunt over the bog's surface with extraordinary precision, catching smaller insects mid-flight. The bog pools beneath them are dark and still, reflecting the sky so perfectly that the water and the air seem to trade places. Then come the birds. In the northern bogs of Scotland, Ireland, Canada, and Siberia, curlews call out across the open ground in long, falling notes that sound almost mournful. The golden plover nests directly on the peat surface, its speckled feathers blending so well with the brown and rust of the bog that the bird seems to disappear. These birds have evolved alongside the bog for thousands of years. They know its rhythms, they trust its stillness, and the bog trusts them back in its way. The birds leave behind seeds and nutrients. Their movements stir the surface water. Life feeds life in the slow, patient way that bogs have always worked. When evening comes, the bog shifts again. The air cools quickly over open water. Mist rises from the pools, thin and white, drifting just above the surface. In some bogs, particularly those near coastlines, this mist can gather so thickly that the entire landscape disappears into soft gray. Ancient travelers feared this. They told stories of lights moving through the fog, pale glows that drifted just out of reach. Scientists now know these lights were likely caused by the faint glow of oxidizing gases rising from the peat, a natural chemical reaction that produces a dim, ghostly light. The bog was not haunted. It was simply alive in its own strange way. And here is the thing that is easy to miss. Standing at the edge of a bog in the fading light, every atom in that dark water, every carbon molecule locked in that peat, every hydrogen atom in that rising mist, all of it has been somewhere else before. Carbon that now sits in a 10,000-year-old layer of peat was once part of a living plant. Before that, it floated in the atmosphere. Before that, it may have been part of the ocean. Before that, it drifted through space, forged in the heart of a star that died long before our sun was born. The bog holds all of that. It holds time. It holds the sky. holds the deep past and the slow future, all compressed into layers of dark, wet earth that gives slightly underfoot when you walk across them. You are standing on something ancient, something patient, something that has been quietly doing its work for longer than human memory reaches. The drip of dew, the exhale of the earth, the soft pop of a methane bubble at the surface of a still, dark pool. The bog breathes, and so do you. The bog does not hurry. It never has. While cities rise and fall, while rivers carve new paths through stone, the bog simply waits. It builds itself one thin layer at a time, one slow century pressed against another. That patience is not emptiness. It is a kind of wisdom. Think of what a bog holds. Pollen from forests that vanished 10,000 years ago. Seeds that no living person has ever seen sprout. The soft outline of a leaf from a tree that grew before any human walked this land. All of it resting quietly in the dark, cool water, perfectly kept. The bog is not a place where things end. It is a place where things are kept safe until the world is ready to understand them. Scientists call Peat Bogs one of the most complete natural archives on Earth. Nowhere else can we read so many chapters of the planet's story in one place. A single meter of peat can hold thousands of years of climate data, preserved in the chemistry of ancient plants. Researchers can look at the pollen layers inside a bog core and watch ice ages come and go. They can see when volcanoes erupted far away. They can trace the slow spread of human farming across a continent, all from a column of dark, quiet earth pulled from a wetland that most people would walk right past. And yet the bog asks for nothing in return. It does not announce itself. It sits at the edge of things, in the low places, in the fog. It breathes out a faint smell of earth and rain. It holds its water close. It keeps its secrets gently, the way a very old and very calm thing tends to do. Somewhere right now, a bog is doing exactly what it has always done. Rain is falling on a cushion of sphagnum moss, that soft, spongy plant that builds the bog from nothing. The water is soaking in slowly, moving down through layers of peat that were alive before your grandparents were born. Small insects are resting on the surface, A dragonfly, wings still, sits on a cotton grass stem. The cotton grass is white and soft, its seed heads floating in the still air like tiny clouds that forgot to rise. The sky above the bog is wide. In the northern bogs of Canada and Siberia, that sky can stretch for hundreds of miles without a single building to interrupt it. The stars come out over those bogs in great sweeping arcs. The Milky Way, our own galaxy, turns slowly overhead, a river of ancient light. And down below, the bog holds its carbon, its water, its long memory, completely still. Our planet is a small, quiet place in a very large universe. It orbits an ordinary star, one of roughly 200 billion stars in this galaxy alone. And yet, on this particular small world, in the low, wet places between hills, life found a way to build something extraordinary. Not with speed, not with force, with patience and water, and the slow, steady work of tiny living things. The bog connects to everything. Its water feeds rivers. Its carbon shapes the air. Its preserved pollen teaches us what the world once was. Its sphagnum moss holds more water than its own weight, and that water keeps the whole system alive. Pull one thread, and the whole picture shifts. That is how this planet works, always. Every system leans on another. Every quiet corner of the earth is doing something that matters. You are part of that too. Right now, breathing slowly, resting, you are part of a world that has been building itself for 4.5 billion years. The iron in your blood was forged inside a star. The water in your body has cycled through oceans and clouds and rivers. And yes, perhaps through a bog somewhere long ago. You are not separate from any of this. You are made of it. The bog will still be there tomorrow. It will still be building, still be storing, still be keeping its long and patient record of everything that has passed. The moss will grow another fraction of a millimeter. The water will hold another day of rain. The earth will turn as it always does, carrying its bogs and its oceans and its sleeping creatures gently through the dark. Rest now. The planet is watching over things. The bog is patient. The stars are steady. There is nothing you need to do tonight but breathe and let the world hold you. Subscribe for a brand new Earth topic every night. and something wonderful is waiting for you tomorrow. Sweet dreams.